So hi everyone, welcome to the TFR Camp Colloquium. It is a pleasure to introduce Professor Dootika Vats from IIT Kanpur. She'll be telling us about Markov chain Monte Carlo methods, giving us a gentle introduction. Over to you, Dootika.
Thank you, Nishant. Right, so yeah, as Nishant has explained, I'm talking about Markov chain Monte Carlo today and giving you a gentle introduction. So two caveats to the talk. So it's designed basically as an introduction to MCMC, as the title says. So I'm really not talking about any of my works per se, but just introducing the topic, particularly because I'm really not a mathematician. I don't really consider myself a mathematician. I'm a core statistician. So if I were to talk about some of my research, potentially a lot of sort of fundamental concepts I might have to sort of explain, fundamental in statistics. So I decided I might as well talk about introducing the topic of Markov chain Monte Carlo. The term gentle over here is particularly chosen because I'm trying to not really go into a lot of math and just give as many visualizations and intuitions as possible. However, if somebody is curious about the underlying mathematics, then I would be very happy to talk about it during or afterwards or later at some point. Please feel free to unmute yourself and ask questions, shout at me if I'm going too quickly or if something's unclear. And of course, you can utilize the chat box as well, and I'll try to see it, or maybe Nishant can, if it's a pertinent question, feel free to interrupt me to say it out loud. Okay, so the focus of the talk today is essentially on the introduction of this problem of sampling. Now, I wanted to differentiate sampling from fundamental sampling in statistics, which is coming from survey sampling and people asking questions out to folks in the world and sort of gathering data. That is called fundamental sampling. What I'm talking about is not fundamental sampling, but rather computational sampling. Okay, and so that's what I'll be focusing on today. Essentially, the problem is that I want to draw samples from a distribution, right? So there's a probability measure, and I want to draw realizations from that distribution. So we consider, for example, there'll be two sort of ongoing examples I will keep along. They're pretty standard. One is the standard Gaussian distribution. So that's the regular normal 0, 1, 0 implying the mean is 0, 1 implying the variance is 1. Okay, so that's the regular distribution. Consider this sort of target distribution. Okay, the idea in sampling is that sampling from normal 0, 1 implies that we want realizations of random variables x1, x2, x3 up until some xn, where I've chosen an n, so that each of the individual xi's has the distribution normal 0, 1. Right? And they're exchangeable in the sense that there's no sequencing, there's no ordering to any of them. They're just realizations from this target distribution, a Gaussian, standard Gaussian distribution. Notationally, I say xi sim n01, as in xi follows normal 0, 1, as in the distributional property of any of these random variables is a standard Gaussian. What ideally we want in computational sampling is we want to draw independent and identically distributed samples, or IID samples, from a given target distribution. In this example, for instance, it's a standard Gaussian. And the independent implies that each xi and xj are independent from each other, as in they basically have nothing to do with each other. Of course, there are formal definitions of independent, and I'm not really talking about giving into the theme of being gentle. I'm not really talking about the definitions mathematically here per se. Okay, but xi and xj are distributionally exactly similar and have nothing to do with each other. Okay. So let's see what I mean by drawing a sample from a standard Gaussian. So N01, this has a distribution, and the distribution has a density function f of x equals 1 over square root 2 pi e to the minus x squared by 2. The 1 over square root 2 pi makes it so that when you integrate this over all reals, this integrates to 1. Okay. The idea over here is that if this is my target density, I'll be drawing points randomly from all of R's, right? that follow this law, follow the law of the Gaussian, standard Gaussian distribution, which implies when I sample from it randomly, I should see a lot of points arbitrarily being sampled in this area. And then some points may be here and some points may be here. But beyond this, I don't really expect any points to be sampled. So if I were to just randomly sample, over here it says x1 because this green dot is x1. If I'm going to start the animation here, this will keep giving me different points, x2, x3, up till some x20, up until this particular, whoops, there you go. Up until this particular slide over here, which says, okay, all of these green dots on the x-axis are sampled points for the Gaussian distribution. IID, as in they're all independent from each other. They're exactly identically distributed. And from these sample points, I can make an approximate estimated density function that tells me approximately what sort of a distribution do these follow all together. And that gives me this blue curve that is that sort of tries to mimic the underlying true black curve, which is the density function. Now, just for the students in the audience, potentially, if I could get some participation as we keep going along, that would be great. So we expect this blue curve to look very similar, to look like the black curve, but why do we not see them overlapping exactly here? So could somebody help me answering to answer that? So why do we see that the blue and the black don't coincide exactly? It's open to non-students as well, of course.
So maybe I don't understand. How do you exactly draw the black curve? You drew some points to start with, and then you drew some curves.
So the black curve to begin with is just e to the minus x squared by 2 1 over square root 2 pi. So it's just the true underlying density, right? The blue curve, which is an approximation of this, right, is from the, if I can get, is a kernel density estimate, which I don't really want to get into, but it's basically looking at the collection of points and then seeing where do we have a lot of points and where do we have a small number of points, and basically mapping these collection of points to the best fitting density curve for this problem, if that makes sense. So basically think of it making really small bins and then going up to the density corresponding to those really small bins.
So there's a student, Prerna Biswas, who has an answer. She can unmute
exactly
and say it herself. Do you want to do that, Prerna?
I'm happy to read it out. So Prerna's answer is that the sampling is not infinite, which is exactly what the point is. This is a random process. I'm getting 1,000 random draws from the underlying Gaussian. And so every time I make this, because I don't have infinite samples, I can't get to the true density every time. But again, I can get to an approximation reasonably okay if I get large number of samples. Okay, I just wanted to make sure I sort of get some response on the randomness, me being a statistician and loving randomness. Okay. So now the question is, how does the computer sample these things, right? So as you can imagine, getting these draws from the standard Gaussian requires me or somebody else to train a computer to sample from this Gaussian using some algorithm. Right? Because it doesn't quite know what a distribution is and what the underlying measure is and what the density function is and so on. So these sort of problems of sampling from a distribution can be categorized into something called computational sampling, or sort of more commonly even just Monte Carlo. Right? And so I will be talking about particularly Markov chain Monte Carlo. But why do we need Markov chain Monte Carlo is why I want to introduce a little bit of the regular IID sampling as well. Okay. So to sort of get to the point of seeing the need of Markov chain Monte Carlo, we look at a slightly different example. Okay. Let's consider now a new example of sampling uniformly from a circle. Okay. So we have a unit circle which is centered at the origin. Which is centered at the origin, and I want to sample points uniformly from this circle. Okay. Now, what I'm assuming is I can draw points quite easily from within a box. So if I have any given box, oops, I can't see my mouse for some reason. Okay, there it is. If I have any given box, something like this, I can draw points uniformly from this box without much fuss, because I can draw points uniformly on this x-axis from whatever 0 to a or some B to A and from some C to D. I can draw a point uniformly from here, and I could draw a point uniformly on the y-axis and join them together, making a tuple point that's uniformly on the box. Right? And so this part I can do. I can sample points uniformly on the box, no issue. Okay? So what I'll do is I'll use these properties of sampling uniformly from a box to sample from a circle. And the way I'm going to do it is I'll take my unit circle that's centered at 0, 0, and I will encapsulate it inside a perfectly fitting square. Okay? And then I will sample uniformly from the square. Uniformly, just without favoring a region of the square over another region, just sample points uniformly from the square. If that sample point turns out to be in my circle, that's a great point. That's a point I want to keep because that's a point from my circle. Right? And if that point turns out to be outside the circle, then that's a point I don't like. That's not a point representing my desire to sample uniformly from the circle. So I discard that point. Okay? So I can run something like this. So for example, here, I have a blue point over here that's inside the circle, so I accept it. And then I sample another point, and that's right about in the circle, so I accept it. And then I can keep doing this and keep accepting until, whoops, I get a point that's outside the circle. And I've coded that in red saying that's not a good point. And I don't want to accept it, so that's not accepted. And I can keep doing this, right? And it's going everywhere. It's just sampling points randomly from the box and then deciding whether to keep it or not, right? And I can do this about 10,000 times. And all the points that were rejected are, of course, in red. All the points that are accepted are in the blue. And what I have at the end are uniformly sampled points from the circle. Now, there is a mathematical proof that's straightforward to see why these are uniform. And intuitively, you can see why they're uniform. It's a uniform box that's underlying over it. You just put a circle on top of it. So you get uniform points in the circle. Okay, all right. Now, let's look at this a little bit in more detail. So in that particular example, what was the probability of accepting? So if we notice, there were a few points that were rejected and a few points that were accepted. And the rate of rejections was fairly low. I mean, the number of red points didn't seem that high compared to the number of blue points. Okay? So particularly, can we have a guess on what could be the probability of accepting a point in the previous example?
Area difference between circle and the rest.
Yeah, exactly. It's a function of what is the area of the circle proportional to what is the area of the underlying box, right? And so that's exactly what the probability of accepting is. It's the area of the circle divided by the area of the box, which turns out to be now pi over 4, which is 0.78. So about 3/4 of the points that 3 out of 4 of the points that I propose will be accepted, right? And 1/4 of the point will be rejected. So that's not that bad, right? That's not that bad in terms of how we're doing. Let's push this idea a little bit. We can repeat this now for a p-dimensional ball and encapsulate the p-dimensional ball in a p-dimensional cube, right? So now instead of a circle and a box, we can take a sphere, a p-dimensional sphere maybe, and put an exacting cube right around it. Now what happens is the area that is the volume of the cube that is not in the volume of the sphere really grows, right? And the ratio of the volumes really expands. So which means, contracts, which means the probability of accepting is the volume of the p ball divided by the volume of the p cube. We sort of know the curse of dimensionality, etc. And so this becomes, pi to the power p by 2 divided by this gamma function times 2 to the p. That's all fine. So let's put in p equals 15. So a 15-dimensional p ball, so a 15-dimensional ball, and we want to encapsulate in a 15-dimensional cube. Turns out that the probability of accepting is 0.0000116, okay? Which means that 1 out of every 1 lakh draws will be accepted. This is just to get 1 acceptance from the circle, right? Remember here in this plot over here, we did 10,000 acceptances, 10,000 blue points pretty quickly. And now we'll have to draw 1 lakh points or 100,000 points from the cube in order to get 1 acceptance on average from the sphere. That seems like quite a tedious job, right? Something I don't want to sign up for. Right? So thus for this large dimensional sampling in any higher dimension, turns out these sort of sampling methodologies will be way too inefficient. Okay, so what can we do? Can we be slightly smarter? So what if we use the information about a current sample to propose the next sample? Okay, so currently, if I have the same sort of circle I want to sample from, but now instead of encapsulating the whole circle, I just put a small box around around where I am. So the bright green, the parrot green dot is where I am right now. And I put a small little box around it. And I say, okay, now propose a value within this box. And if that value is inside the circle, I accept that value. And if that value is outside the circle, I say, no, that's not a good value, right? And when I let this run, I let this run once, and I see, okay, that this value is accepted, it's in the circle. I keep going, all acceptances, right? And then let me just run this because it's too much clicking. Okay, I get some reds in the middle. Certainly I get some rejections, and it's moving around slowly now. It's not doing the random thing it was doing before. It's moving around in one part of the area, right? But then eventually it will move away. It will move away eventually. And so now when I get 10,000 acceptances, eventually it will cover the whole space. But notice now there are no red dots in these far away corners, right? In the far away corners of the box. Right? And that is because we are using the information of where we are at a particular time, putting a box around it and say, listen, I know where I am. I don't want to overreach now. I mean, it's a high dimensional problem potentially. I don't want to blindly just sample anywhere. I'm going because that turns out to be too inefficient. So I'm going to have to use the information that I have available to me, which is where I am right now. Right? And that turns out to be in higher dimensions. In this problem, there's no reason to do that in the circle sphere problem, in the circle box problem. But in a higher dimensional problem, we start seeing reasons to do that, because otherwise you get samplers that are very, very inefficient. Okay. Now, this obviously has some problems that we could probably see. First question is, why do we know that this is uniformly drawn from the circle, right? What makes it a uniformly drawn points from the circle? And that's a valid question, which is in general, what I'll try and address in this, essentially in this talk. What makes an algorithm like this work and give us points that are from our quote unquote target distribution, right? And the other thing is that we're actually not getting random points, right? So if I go back to the first, yep, there it is. If I go back here and let's let this run a little bit more, I see that these points are obviously correlated with each other. Remember, I wanted independent and identically distributed points, right? And maybe they are identically distributed in the sense that all of them are from this distribution, which is the underlying uniform distribution on the circle, but they're certainly not independent, because the next straw depends on where I am, because I'm making the box around where I am currently. Okay? So naturally, this leads us to the idea, well, we're dealing with a Markov chain over here. We're dealing with some sort of a Markov chain. And that's why this sort of idea of sampling, using a current state to get the next state, leads to this idea of Markov chain Monte Carlo sampling. We're doing Monte Carlo sampling, but we're doing it using a Markov chain. Okay.
So just a question about terminology. When you say Monte Carlo sampling, that just means IID samples from the distribution that we care about. And when you say Markov chain Monte Carlo, it just depends. The next thing that you pick depends on the previous state or your present state.
That's exactly right. Now, the term Monte Carlo is slightly more, has a lot more usages out in the real world. I mean, of course, the city itself, but out in the real world, in the sense of just averaging anything, any sort of random draws, averaging is sometimes also called Monte Carlo. But within this field of sampling, getting IID draws is typically called vanilla Monte Carlo or just Monte Carlo.
Thanks.
Yeah. Okay. So capital F now is, I'm going to start using some notation. So capital F is my target distribution, and it's defined on some state space script X. Now, often when students particularly read about stochastic processes and Markov chains, they're on discrete state spaces. As a statistician working in this area of Markov chain Monte Carlo, I'm rarely looking at discrete state spaces. I'm typically looking at general state spaces. So if you're looking for the definition of, a Markov chain transition matrix, etc., we're not going to have matrices here at all. We're going to have kernels instead of matrices. So just giving you a heads up to be ready for what looks like weird definitions. Now, the goal is to sample from F. F could be the Gaussian distribution, which again is a general state space distribution. It could be the distribution of, which is the uniform distribution over the circle or the sphere, etc. So in MCMC, we construct a Markov chain such that capital F, our target distribution, is the stationary distribution of that Markov chain. Now I'll define and show you what I mean by stationary distribution via a visualization and a definition. And then basically the steps of the Markov chain, how the Markov chain progresses, is then determined by the Markov chain transition kernel. So that given a point X in my state space and given a nice set A, now I can't talk about moving to another point Y, because now this is a general state space and I can't really measure probabilities of going from one point to another point Y, but I can measure probabilities of going from one point to a set. Right? So starting from a point X in my state space to a nice set A, the Markov chain transition kernel is denoted by Px comma A, which is just the probability of that the next step, given any xk step which is equal to x, the xk plus first step is in the set A. Right? Now, this basically different ways of obtaining and constructing such transition kernels will give us different Markov chains and will give us different sampling algorithms. So you can sort of define how this evolution of the Markov chain will change, and that will give us a new algorithm. For example, in this sort of animation, I can't show it to you here, but if I can increase or decrease the size of the box, and that will give me a new transition kernel. Right? Because the way I'm sampling from one state to the other state is changing, because the places where I'm actually drawing values from is changing. Right? So the kernel changes. The key to MCMC, or Markov chain Monte Carlo, is to construct good kernels, where good I should have put in quotes, good or nice kernels P, so that we can obtain again nice samples from F. Okay, so that's the goal. What's sort of flipped in MCMC that's different from general studies of stochastic processes is that we know F. We know F. We're not given a Markov chain and trying to find out what the stationary distribution is. We know what we want our target distribution to be. We're trying to construct Markov chain kernels that are good and have good properties. Okay. So let's look at one particular such algorithm, the most popular one, which is called the Metropolis-Hastings MH sampler, or an algorithm. Okay. Let small f be the density of capital F, and let us choose. So we're choosing, and this choice is critical. We're choosing a kernel Q, which is called the proposal kernel. Okay. This Q is what was our box in the uniform example, in the uniform sampling from the circle example. And this Q, capital Q kernel, has an associated density small q. Now, this kernel Q, is the proposal kernel, will depend on where I am right now, right? Because it will, for example, the center of the box was where you were at that particular point. Right? And to simplify things, we'll assume that Q is symmetric in the sense that Qx comma y is equal to Qy comma x. Now, this is not a necessary condition. It's just much simpler if we just assume this for the purposes of the talk today, just cleaner notation. Okay, so given a current step xt, the MH algorithm updates in the following way. It proposes a value y from the proposal kernel Q given a particular point. So if I'm over here in the circle, and if I'm over here, this square is my Q, and any proposed value that I propose in this box, this can be denoted as y. It's a random draw uniformly from this box. Now, what I calculate now is this alpha quantity, which is the probability of acceptance, which is the minimum between 1 and the ratio of my target densities at the proposed point and at the previous point. Okay, and the intuition will be slightly more clear in the next slide. Basically, the idea is that if my proposed point is in a higher density area, then I want to accept it more often. Right? It's in a higher density area than where I'm currently at, then I want to go higher in my density area, because when the density is higher to a particular area, those areas are where the mass of the distribution lies. Right? And if the proposed value of y lies in a lower area of density compared to where I'm currently at, the probability of moving there, I want to be lower and not as much. Okay? That's basically the idea. Now, here's the main critical step. Once you calculate alpha, you set x t plus 1 to be equal to the next step to be equal to your proposed value with probability alpha. But with probability 1 minus alpha, you stay where you are. Okay? So you say, okay, I'm not going to wait around, there is an acceptance. My next step is my previous step. Right? So it's like a hop. I either jump somewhere else or I hop where I am. Okay. And so it's possible sometimes we'll just keep staying where we are for a while until we accept, and that's okay.
So Dootika, I'm a little bit confused. So what is alpha again?
Alpha is the minimum of the density evaluation. So this small f is the density of the target function, target distribution. So let's consider a Gaussian density. It's difficult to look at
sure, because the uniform, is uniform there.
Exactly. So let's look at the Gaussian density. So let's say, and then this is the next slide. If I'm, let's say here, this is my xt at my current time point. I basically will look at my evaluated density point here, and let's say this is y. I propose y, right? And so this is f of y, the density value at that point, the value of the density. This is xt. And so turns out y I propose in a higher area of the density, right? So that means I'd actually want to move towards y. Those areas are where I want to go compared to xt. Sure. So I have a larger chance of moving there. In fact, in this case, I will certainly move there, right? Because it's with probability alpha. Now, if this is my xt and now this becomes my y.
I see. Right? I see.
Now I don't want to move there that much. Yeah. So it's not a zero probability. I'll still move there, but I'll move there with a smaller probability.
So there's a small confusion which has also been mentioned in the chat. So what is the difference between small f and capital F? So small f is the density induced by our target distribution f. So it's more or less, I mean, I don't want to get into sort of measure theoretic descriptions of these things, but you can just think of f as the distribution family of just the normal 0, 1. The f tells you where, f basically tells you how much mass is given in which regions, but small f is the density induced by f, in the sense it tells you exactly what the function looks like at a granulated scale of the axis. This is certainly not a technical definition, but this I'm just being careful in differentiating between the density and the distribution, because these are two different things. Right? So if I want to, for example, for the Gaussian density, if I want to measure what is the mass associated with the interval -1 and 1, I will have to sort of write -1 to 1 f of x dx, and that becomes, f of the interval -1, 1, the mass associated with this interval. Okay, so that's just me being careful between the distribution and the density. Okay. Right. So what is an example of a kernel Q? Great. So let me move this. So whoops. In the circle example, Q was the small uniform box centered at xt. So notationally speaking, Q becomes, I can annotate. Yeah. Notationally speaking, in this example, this was Q. Q was one uniform.
Can I interrupt you for just a second?
Sure. Yeah.
Yeah, this is Sivaguru here. I think there's a question in the chat which I think I also share. Could you give an example of the kernel Q?
Yes. That's what I'm currently writing. Yeah.
Oh, okay. Yeah,
So,
thanks.
yeah. So in this particular circle point, so if this is my center x t at my current point, I'm creating a box. So the box is xt minus some h and xt plus some h, xt, the first component of xt, times uniform xt, the second component of xt minus some h, xt second component plus some h. Okay. So the xt now is a tuple because it's a two-dimensional problem. xt1, xt2. Right? Okay.
So just to be sure that I'm on the same page, don't you want to sort of put an indicator function for the disk as well? Sort of remove the points, or the kernel doesn't?
The kernel doesn't. The kernel doesn't. So
doesn't
that the
reject
kernel
points.
doesn't, because f rejects points, because f, the mass, there's
Goes to
no
zero.
mass
Yeah,
outside.
sure.
Exactly. There's no mass outside the disk, so it goes to zero. So those points will never be accepted. That's a great question. A great point, I should say. Those points will never be accepted because there's no mass associated anywhere in this area.
Yes, I have one question. Like how we are choosing the Q kernel function?
Yeah, that's a great question. There is no universal answer to this. This is, I mean, you choose different kernel functions, you get different research papers, you get different algorithms. You know, this is a continual area of research. I'll show you another instance of another example in the next slide, and then maybe we'll sort of get some clarity as to another example. Okay. Oops. Okay. So this is now a MH, or a Metropolis-Hastings, for a Gaussian example where my kernel is, my kernel is normal x comma 4. Right? That means wherever I am is the mean of the kernel, mean of the proposal kernel, and the variance is 4. Okay. So what does this look like? Here I keep going back and forth. The green point is my current point x. Okay.
Hi, Dootika. We lost you for a minute.
Yeah. I think that was that's my internet. Okay, you were back on?
Yes.
Okay. Perfect. Sorry about that, guys. Okay, so let's go back to this. So we're
So right now we don't have a small f or a capital F. We just have a Q and.
Sorry. No. We have a small f. The small f of x is still 1 over square root 2 pi e to the minus x squared by 2. The target distribution f is still normal 0, 1. Yeah, thanks for pointing that out. Okay.
Just another question. If we can already use something like normal x4, then wouldn't we automatically get, like, we wouldn't have to do this, right?
You're catching my lies before I can actually do anything. Yeah, this is a toy setup, right? So this is a toy setup, of course.
Sure.
We can already sample from normal x comma 4, and so forget. Let's assume a higher authority is somehow giving us these Q draws, and we personally have no way of getting to them. So it's just a toy example, yeah. Okay, so the green point is where I am. My God, stop moving. Thank you, please. Yes, thanks. And so the first thing I do is get my Q kernel, right? So this is in the green shaded density function. That's the density of a normal distribution with mean x where I am and variance 4. And then I propose a value from this kernel. That's this blue point over here. Blue means proposed value. Now it's going to look at the density function associated at that point under the target. So it'll go vertically upstairs until it reaches the black curve. And we see that this blue point is in a low area of probability compared to my green point. Green point is in higher area. So now it's unlikely to accept this point. I have a feeling we're not going to accept this point. So let's see. Turns out I coded it in red. That means it was rejected. So that gets thrown away in the sense that the next step is going to be where I am currently still. So this is my next step hasn't changed. I am where I was. Xt plus 1 is equal to xt. Okay. Then I do this thing, the whole spiel again. Same proposal kernel because I haven't moved. I propose a new value now, random value. Now I'm again in a slightly lower area that is being proposed. So I'll do this again. It turns out, whoops, did not accept it, still rejected it. Okay, I do this again. I will likely still reject it because again, it's in a low area, right? I did this randomly. So now I'm just dealing with the consequences of being honest with my simulation. And now finally, nope, still very low area of probability, not going to accept it until hopefully very soon, there we go. We've proposed a value that is in a higher area under the target black curve, right? And so now we're certainly going to accept it. It's not like we'll never accept points that are far away. We will accept those points, but not as frequently. And now this will be coded as green. And now we move. Our next proposal now moves our means because our proposal is always centered at where we are. That's the kind of proposal that we've chosen. Okay. And I can keep sort of doing this and it'll keep moving and changing based on where it's proposing values and what sort of values it's accepting, right? Finally, at the end, hopefully soon enough, what we get are the green points are all the points of the Markov chain. Some of these are accepted points. Some of these are points that got rejected, but now we're at where we are, right? And I have now made the same sort of kernel density, approximate density curve from these points from 1000 samples. It's not perfect, but it looks reasonably okay, right? Now, why does it look reasonably okay is what we'll get to in this next part of this. Hopefully, I'll have a little bit of time to get into that. Okay. Okay, there's something in the chat box, maybe.
I have a question. So what is the blue curve?
Yeah. So the blue curve is the approximated density from all of these black points. All of these green points. The green points that are my Markov chain, that are the realization of the Markov chain. It is the approximation of, okay, given where, so the blue curve essentially means that in the middle, there are a lot of points. Now, because these are all overlain on each other, I can't really show it to you, right? So think of it as a histogram where the histogram's underlying part has gone away and you just have the density.
I see. It's the superimposition of the Qs for those points, is it?
Not really, no. So it is basically, so think of just a histogram of all of these green points, right? So is that something that's okay? Yeah, so instead of drawing a histogram, I've drawn an infinitesimal discretization of that histogram.
Okay, thanks.
Okay. It's one of those things where I'm talking to a statistics audience. I don't think twice about drawing a approximated density, and now I should have thought about that a bit more. Okay, I'm done with the simulation. I will stop my annotation as well. Okay, great. Okay, so now the thing is that what's happening in my Markov chain, let me go back one slide. Okay, so the initial value of the Markov chain is something I have to choose, right? The next step, every subsequent step is okay as long as I have my Markov chain transition kernel, but the first step of the Markov chain has to be chosen by me as well. So I have to choose my proposal and I have to choose the first step. Now, if the initial value x1 is drawn from f1, some starting distribution, I just call it f1, and it could potentially be not f, right? Not sampling from f. Then the question is, I have the conditional distribution of x2 given x1, but what is the marginal distribution of x2? So the marginal distribution of x2 is the fact that we're starting from f1, right? Integrating over all possible choices that I could have started from f1, and then moving from this chosen x to any of the y's, right? That is the marginal distribution of the realization x2 as the Markov chain moves. And this f2 may not be equal to f. Okay? And I can keep doing this. The f3 may not be equal to f. f4 may not be equal to f. Okay? The problem now is So thus, in general, this Markov, the marginal distribution for each of the draws, F sub t is the marginal distribution of all the realizations of the Markov chain may not be equal to F. And this, of course, is not good news because I want to sample from F, right? And I'm getting draws from F sub t, which are different at each time point. So how does it help us? So the first thing is what happens when F1 is equal to F. That's something I want to first figure out. If I were to start from F, then what happens? Right? If I can give it a starting value that is a random draw from F, then what happens? That is what is a property of stationarity, where if I can draw from F and then use that as a starting point, and if I get back F, then that means the kernel I've chosen is F stationary. That is, if I draw anywhere from F, and then using that X drawn, go to anywhere in dy, the distribution of that is just F itself, right? Integrating over all possible draws from F. So if I start from F, then every step of the Markov chain will yield a draw from F. Now this is pretty cool, right? That means that now, this ensures if we can get one representative draw, just one draw from my P ball, right? From a P ball in the uniform distribution over the P ball, or one random draw from Gaussian, I can take that and run with it as long as my kernel P is stationary, F stationary, right? So X1 is from F, that's chosen by me. And then I run my P kernel, and then that gives me X2 from F, X3 from F, Xn from F. This is the property that not unique to Metropolis-Hastings, it's unique to a lot of other Markov chains as well. But the Metropolis-Hastings alpha acceptance function ensures that this property holds true. Okay.
Can I ask you a question?
Of course, yeah.
Sorry. So is there a measure theoretic or some kind of Hilbert space analog or way of phrasing this? I mean, I don't work in probability or statistics, but it sounds like there's probably some version you can phrase it that might make it easier for some of us to understand.
You can think of these as linear. You can think of the Markov chain as a linear operator, working on that Hilbert space as well. It's not a, and then basically every subsequent step of the Markov chain is then just a outer product. It's just an inner product of this linear operator with some desired function F. It's not an interpretation that I'm very familiar with because I'm sort of more used to the probability and statistics side.
I see. Okay, thanks.
But there is
this thing almost looks like some kind of reproducing kernel on some appropriate space, right?
Yeah. So you can think of the Markov chain transition kernel as basically a linear operator, and that sort of has a very similar. There's like a whole sort of study of Markov chains as linear operators from the point perspective of MCMC as well. But yeah, I'm not too familiar with that.
Okay, thank you very much.
Yeah. Okay. Now that means that we can get samples from F if we can start from F, but they're not independent samples. So I'm not really like very excited in life right now because these are correlated samples, right? And I said that I want IID samples, and that's something that's going to be a utopian idea of getting IID samples in high dimensional is quite complicated. Okay. But let's see a visualization for stationarity. So I'm all for visualizations to try and see if we can understand what's going on. I will warn you up front, there's going to be blue density curves here as well. So this exercise now is purely for visualization and not really what is done typically in MCMC algorithms, right? But because I'm giving you a toy example, I can sort of give you sort of toy visualizations. So what I'm going to do is repeat the MH algorithm some capital R times, okay? So every row of this right now is a Markov chain, is a Metropolis-Hastings algorithm. Every row over here is one run of MH, right? I get the first run is the superscript is the run that I'm talking about, and the subscript is the time of the Markov chain, the discrete time of the Markov chain. The first draw is from F, right? Because I want that for stationarity. I want to draw from F. Right? And then I just run it. I just draw a random draw from a standard normal, let's say, and then I just run my Markov chain kernel that I showed you previously. right? With the proposal that I had chosen before. I just run it. But I do it r different times. Okay. The reason I'm doing it r different times is what I want to look at is I will look at the columns of all of these. Right? In the columns, what I get are, because these are independently run, each of these Markov chains, I will get r IID draws from F, right? Because recall, x2 is from F up till xn is from F, because my Markov chain is stationary. So each of these draws is from F, but in one row, I don't have IIDness. Okay? But in one column, I have IIDness because these are independent runs. Okay? And so what this will allow me to do is look at an approximation of F1. And is it equal to F? I can check. This will allow me to look at an approximation of F2, the marginal distribution of the Markov chain at time 2, and check, is it equal to F? This will allow me to look at the marginal distribution of the Markov chain at time point n, and will allow me to check, is this visually looking like F? Right? This is really what I'm trying to do. Okay. Okay. Get rid of these. Okay. So now let me do the same thing. So now in the blue curve is my approximated density from multiple runs that I'm showing you from F1, from the starting distribution. This is from now F2, now from F3, and I'll just keep running this up until F some time point. And we look at like all of these blue curves are essentially statistically similar to each other. There's randomness, of course, because this is a random process. But when I overlay all of them, they don't really look, there's no trend. They look like they're very similar, statistically similar to each other. Right? This demonstrates stationarity for me. The fact that I'm starting from F and then I'm retaining F as I keep going along. Okay? But what if I don't start from F? And certainly, if we can start from F, that means we can go and sample from F also. IID, right? If we can get one unique draw from F, then I can go and keep doing that and just get many draws from F. So typically, I can't draw from F. It is almost, I said impossible, but very difficult often. Okay? Which means that F sub t, the marginal distribution at time t, is not equal to F for any t. Okay. So then this leads us to the idea, wait, do we get anything useful? And we do. We get something useful because the Markov chains we construct in MCMC, the Metropolis-Hastings, for instance, are carefully constructed using constructed basically to ensure that the Markov chain is F-ergodic, which means that as t goes to infinity, for any starting distribution, you can choose whatever starting distribution you want, F1, right? For the first draw of the Markov chain, the marginal distribution at time t is going to converge to the target distribution F in total variation distance. The TV distance is a distance on measures. So it's going to converge to F as t goes to infinity. Okay? Which means that no matter where we start from, we can sort of blindly start from a starting point. Eventually, right, we will obtain samples close enough to F. Right? And when that eventually happens, depends on how good your Markov chain sampler is. So let's see this in a visualization again. Now, when is the Markov chain F-ergodic? I'm not going into this because again, this was a gentle introduction. So Markov chain is F-ergodic if it is F-irreducible, aperiodic, and Harris recurrent. Okay. I'm happy to discuss sort of references and resources where you can learn more about this, but I'm not really going into these definitions. We repeat this for visualizing ergodicity. We repeat everything as we did before, except now I'm being careful as to not to start from F. I'm starting, let's say, from a point mass at -1. Right? F1, my starting measure, my starting distribution is fixed at -1. So all of the R replications are starting from -1. Clearly a bad starting distribution, right? Because it is not normal. The Gaussian distribution is our target, and our starting distribution is a fixed point at -1. It's a point mass. Okay. And we do the same visualization we had done before. Oops. So now the density estimate at this point, the density estimate is pretty bad because it should just be 1 point mass, but R can't really do that very nicely. So it just gives you a very thin curve at -1, at -1. And then I'll run this. What is the distribution at F1? Okay. Then what is the distribution at F2? Right? At marginal distribution at time x2. I see it is sort of moved away from -1, the fixed point mass at -1. And then at F3, at F4, and I can keep running this. And now it's sort of come down to my standard Gaussian target distribution. So at some time, let's say, let's say 1, 2, 3, 4, 5, 6, maybe not 7. Yeah, maybe about 10 or so. At time 10, I'm close enough to my target distribution. Right? So when I said eventually close enough to the target distribution, here, I mean, this is not actual science because I'm just eyeballing it. I'm right now saying that about 10 or time step 10 or 11, I'm pretty close to my target distribution. Right? And this is the evolution starting from point mass up until in 50 time steps. What does the marginal distribution start looking like? Okay. I can repeat the same thing again, but now my starting distribution is 4. Is a normal Gaussian distribution, mean 4, variance 0.01. Okay, so it's a random distribution. It's not a fixed point mass. And I do this again, and now the variance is slightly smaller, but still I'm sort of very quickly coming down to my target distribution, right? Pretty quickly in about, again, 10, 15 steps. Right? So it's sort of, I'm starting a bit far away now at 4, but I'm still able to, in a few steps, come to my starting distribution. So if I were to pick up the points at time 2, time 3, and time 4 for any run of the Markov chain, those are not going to be representative points. But points at time 50 are then going to be representative points. Right? So there's an initial bias, but then that drops away relatively quickly in well-behaved Markov chains. Okay. Maybe I don't quite have time left. So feel free to tell me.
Another couple of minutes or so.
Okay, sure. So recall that if we get samples close enough to F, even if we're happy with that, we have samples close enough to F, they're still correlated samples, right? So they're bad samples. I said I was not happy with it. I'm still not happy with it. Are they any good? Can we do anything with these samples? What are we trying to do with these samples? So it turns out if the Markov chain is F ergodic, which we showed that these Markov chains were visually, they sort of were converging, we can do a lot. Suppose we are interested in estimating the mean of the target distribution F. That is, we are interested in estimating theta, which is the integral over the script x f dx. I can look at the sample mean of the Markov chain, of the realization of the Markov chain, and for that, a Markov chain version of the law of large numbers holds. That means x bar n converges to theta almost surely as n goes to infinity. Thus, even though if we have bad samples from the target, they're correlated and only approximately from F. Magic still exists, right? And I can see that. I can see it visually. Here, what I do is I run 20 Markov chains, and I draw the running estimate of the sample mean as a function of my Monte Carlo sample, as a function of my sample size, my n. Right? And in the beginning, they're highly variable, right? And they're all over the place because there's not a lot of samples in the beginning. Right? There's some bias as well. And as I keep going more and more and more samples, I sort of see the law of large numbers kicking in. I'm converging to 0, which is the mean of my target distribution. But I'm a statistician. I'm not happy with just estimating theta. I mean, I can guess blindly theta is 8,000 and go back home, and that's an estimate because I guessed it. But I am interested in what is the variability? How good is my estimate? Now, in IID sampling, I can assess variability if I have something like a central limit theorem holding for the average, right? Turns out, under some additional conditions, which I won't discuss today, on the Markov chain, we can also get a CLT holding, which yields that as n tends to infinity, square root n x bar n, which is our Monte Carlo sample mean, minus theta, our mean of the target distribution, that converges to a Gaussian mean 0, variance sigma squared. Now, sigma squared now is complicated. It's not easy anymore, right? And I'll get to it a little bit later if we have time, but I'm happy to skip that part. then this implies that approximately x bar n is normally distributed, mean zero, variance sigma squared by n, approximately. So I can see that in play here as well. In multiple replications, this is at distribution of x bar at n equals 100, at n equals 200, 300, 400, 500, and it starts obviously because the variance gets smaller and smaller at 1 by n rate. It gets tighter and tighter and more Gaussian-like, more peaky and more symmetric, more Gaussian-like tail. And this I'll sort of keep it starts becoming closer and closer. That means our estimate is getting better and better because of the law of large numbers. The variability as well is getting smaller and smaller and smaller. Okay? Of course, if I were to do a root n multiplication in this, I could see what the actual distribution looks like in terms of the Gaussian. Okay. Maybe I'll not really go into this, the variance aspect. Just a small note, and this is not just a toy to see how the sampling works. Actually, MCMC is like the bread and butter for computation in something called Bayesian statistics, where we have terribly high dimensional, terribly complicated distributions F, that for which the density function is not known completely. It's only known up to a normalizing constant, only known up to some F tilde. And we have to resort to these MCMC type algorithms to learn things about the underlying distribution F. Now, I chose not to talk about this because it requires more statistics backgrounds, and it would be more difficult for me to talk about this, the Bayesian aspect. Okay, so the last slide. So we want to use MC given a target distribution F. Suppose it's complicated, suppose it's high dimensional. Actually, I want to use MCMC only if Monte Carlo, IID Monte Carlo is not possible or highly inefficient, because the correlation is not something I'm looking for. Correlation in the samples is going to give me less and less new information with every subsequent sample, and that's not a good look for me. Metropolis-Hastings, what we sort of, I didn't quite get into this, but we have to choose a proposal kernel Q. Right? And I fixed the kernel for the discussion here, but there's ample amount of work in tuning the proposal kernel, in sort of making the size of the kernel larger or smaller, what sort of acceptance rates are good, what sort of acceptance rates are bad, is Gaussian always good, can we use some other family of kernels, and so on and so forth. So there's a rich amount of literature and research in that part of this. I have also completely skipped over theoretical properties of the Markov chains, reversibility, irreducibility, more detailed study of ergodicity and rates of convergence of the Markov chains. Now, these are things in general state spaces become slightly more difficult to get into because of the fact that you have sort of, you can't really measure the size of going from one point A to another point B. And then the final question that sort of I work in quite a lot is when should we terminate MCMC simulations? We can say, okay, let's run a simulation and wait for lunch, but is that good enough? We can't wait forever. We can't say, okay, infinity is when law of large number kicks in, so let's run it till infinity. Now, we have the luxury of running it as long as we want it on the computer, but at some point, we have to make a decision, and we have to make informed decisions, not just blind decisions. So how is that done? That's an important area of research and a significant challenge as well. Okay, thank you. I apologize if I went over time, and yeah, I'm happy to take questions if we still have some time left over.
Let's thank Professor Dootika Vats for a wonderful talk. I open the floor for further questions.
Okay, let me begin by trying to help the speaker out. Can you say something about the sigma squared?
Yeah, oh sure. You're helping me out as well, because this actually is my area of main area of research. What is sigma squared? So sigma squared is the limiting variance in my process in my ergodic average. So basically, sigma square is equal to limit of n times the variance of x bar n as n tends to infinity. Okay? That's the actual form in reality. Now the issue is, if I look at this term over here, variance of 1 by n of the sum of the x's, turns out because my x's are correlated, this is not going to be just the sum of the individual variances, right? We have variance of x1 plus x2 is equal to variance of x1 plus variance of x2 plus 2 times the covariance between x1 and x2. And when these are independent, the covariance goes away. There's no covariance. Okay? When these are correlated, it very much stays there. So after a sequence of steps, one can show that sigma squared is the covariance, variance under my target f, plus 2 times the covariance of k going from 1 to infinity of covariance of any of the x1s plus x1 plus k. So it's basically what you get from an alpha mixing process, if you're familiar with alpha mixing process literature. So the problem is now there's serial correlation. There's correlation up unto an infinite lag, basically, right? And that's coming from the fact that it's a limiting object, right? As n goes to infinity, right? So there's covariance, because Markov chain has serial correlation, never dies away. So that is something we have to start accounting for. And this really, from a statistical perspective, we want to try and estimate sigma square and learn more about it, because sigma square tells us what is the variability in x bar. Okay? And it becomes challenging to estimate sigma square. And that's really where at least a bulk of my research comes in. Is this helpful?
Thank you. That was actually very helpful.
Any further questions from the audience?
So I had a question. So you mentioned the convergence of the distributions. So are there properties known how fast it converges?
Yes, absolutely. So I didn't really get into it. So because of all the animations, this file is like 10 MB, which I think Adobe just does not like at all. So let me write this expression down again. So we have sigma squared is equal to the first term, the variance, plus 2 times the summation of the covariance of x1 plus k. Right now, this is a infinite sum of quantities, which may not decrease very quickly to 0. I mean, these are because it's a Markov chain. The covariance decreases as a function of k, but it may not decrease fast enough for this sigma square to be finite. So this lends us to sort of really be very specific on what are the rates of convergence. So if you basically get, I mean, in general state spaces, 3 sort of qualitative rates of convergence. You get polynomial ergodicity, which sort of says that the covariance sort of decays at a polynomial rate. You get geometric ergodicity, which sort of says that the covariance structure decays at a geometric rate. You get uniform ergodicity, which says that it decreases at a geometric rate and does not depend on F1. Does not depend on your starting distribution at all. It just decreases no matter where you start from. Now, depending on your choice of kernel and your choice of Markov chain algorithm, you can get one of these 3 or all of the 3 if it's uniformly ergodic, or neither of the 3. There are examples where certain kernels don't give you any of these 3 sort of fast enough rates of convergence, and you don't get a Markov chain central limit theorem holding, for example. So it really depends on the choice of the Markov chain kernel, the Markov chain algorithm, the Metropolis-Hastings construction.
Okay. And one more aspect was you mentioned you can sample from densities even without knowing them completely. That is because your acceptance probability is just a ratio of them?
Yes, exactly. That's exactly right. So in the next slide, I believe, so we have sort of this f tilde, and there is a proportionality constant next to it that is not a function of x. And so when I look at alpha, which is my acceptance probability, which is f by f at 2 different points, the unknown constants cancel away. Right? So whatever is that constant k just goes away, and I don't need it to actually run my Markov chain algorithm. Yeah, that's exactly right. You're 5 steps ahead of me.
Thanks.
Yeah. I think there's a question in the chat. Do we have time? Should I take it, or I'm happy to?
Please go ahead. I guess who all want to listen to the sessions can stay and listen to the answers. Yeah.
Okay. So 2 questions. If you're starting different runs from the same point, is it possible that these might be correlated? So that's a good question. Sort of tricky to visualize. So over here, if we're starting from the same point, they're independently progressing. So the only thing common to them is the starting distribution. But the way they're progressing, I can get to the slide, the way they're progressing is exactly the same. Okay? So they are genuinely independent, because when you run this Markov chain and when you run this Markov chain, there's nothing to do with each other. But the question is, what are the independent runs of? They are independent runs of Markov chains that start from -1. Right? So the commonality is still there, and that defines the world or the distributional property of each of the Markov chains. But they are independent runs of Markov chains that start at -1. Okay? And question is, what is the probability measure? Oofta. I may not want to take this one. It'll require some effort, but you can think again of a probability measure. If you're okay with density functions, I sometimes, with statisticians, I like to go in the opposite direction of starting from a density function. You can think of a density function visualizing what mass is assigned to which area, and you think of a probability measure as describing any subset of this distribution is assigned mass proportional to the area underneath that density function. Now, to the probabilists in the audience, I apologize. That is not a good definition of a probability measure. But if you don't know what a probability measure is, this is the best way for me to sort of explain it to you.
By the way, I think this was very helpful. Are there further questions from the audience?
Yeah, I have one question.
Yeah.
In case of MCMC Metropolis-Hastings, let's say, is there any method to reduce like burning time, or like to reduce like convergence?
Yeah, time to convergence.
Yeah.
Right. So the phrase used by Sandeep, I think, is burning time, which is basically the time it takes to go from a bad starting distribution to essentially converge distributionally very close to our target. So for example, visually here, burning time is about 10 steps, because it took us about 10 steps to come close to our target distribution. To improve your burning time, there are 2 things to do. You make your Markov chain, you tune your Markov chain or Metropolis-Hastings sampler in such a way that it is able to explore the state space in a good way, where it is taking big jumps more often. And 2 is really choose your starting distribution very well. If you can choose a good starting point, which lies in an area of high probability, you'll converge much faster to your target distribution. If you choose a point that's very far away, I mean, imagine starting this Markov chain at 100 and taking sizes, very small steps, right?
Yeah.
Starting from 100, coming to here will take 1,000 steps, for example.
Yeah.
So we have to tune our Markov chain so that it takes bigger jumps, but not too big, because if it starts taking too big jumps, then it potentially will not move at all. And then we have to choose a starting distribution very carefully.
Yeah, for that, like step size, maybe like is there a method to decide that step size?
Sorry, please say that. Could you repeat that?
Like you said, we're not starting from far. So is there like a method to make sure this is not the case?
To find a good starting point, is that your question?
Yes.
Yeah, so it depends. I mean, if you're in a typical Bayesian problem, then starting, the data can often inform us as to what is a good starting point. For example, if max, I apologize, but if there's a maximum likelihood estimate that's available to you, use that, because MLEs will be very close to posterior expectations. So maybe use an MLE. If data set size is small, you can use random draws from the priors or means of the prior distributions. That's something you can use. Otherwise, the best bet is, sorry?
Sorry, continue. I'm saying data size is really big, let's say ImageNet.
Very big. So then starting from something like the MLE, if it exists, you can start that. Otherwise, run multiple parallel runs of the Markov chains and sort of see where it's moving, and then sort of start a fresh run again, where from a place that it likes to stick to. If it likes to stick to an area and sort of travels it nicely, that's a place that has a high posterior mass, so sort of go there.
Thank
Right? So tuning Markov chains and getting it to work in MCMC is an art. I mean, it is a science, but it is also an art in some sense.
Thank you.
Welcome.
I guess there is also an issue, for example, even if you use MLE, if we know that the posterior is not unimodal or it has multimodes, then the maximum likelihood estimate might not be very, I mean, firstly, it may not be unique. So we'll have to do some regularization for that.
Yeah.
And on top of that, once we have this non-uniqueness, our Markov chain will basically be very, because it may not even explore the other high probability regions. And then so I mean, so is there any is there any very new literature on the convergence diagnostics?
So in fact, if you maybe I'll try and see if I can email this, or if you Google measuring quality of MCMC samples, there's a workshop happening by the Bayesian Computation Society on October 5th, 13th, and 22nd, on 3 different days. And it's really the first day on October 5th is a general viewpoint on MCMC diagnostics. So I'll tell you the one. So I'm taking part in the discussion there. I'll tell you the one line for that. The view on diagnostics is that when they tell you everything's okay, you can't believe it. When they tell you something's not working, then believe it, right? So if a diagnostic says something's messed up, it's genuinely messed up. If it tells you all's nice and cozy, don't believe it. I mean, always be insecure about your Markov chains. Completely, just absolutely insecure about the Markov chains. I wish I had a better answer, but we're statisticians, so what's unknown is unknown.
Right. Yeah.
Right. The lights are off, and we're walking in a room, and we're treading extremely carefully all the time.
That's right. Yeah. I mean, in most of the scenarios, the capital F may not really be known to us.
Yeah,
so,
and it's in high dimensions, right? So exactly. we can sort of visualize this one-dimensional density, but in 15, 20 million dimensions, I mean, all hopes are not all hopes, but most of the hope is gone.
Right. Yeah. Well, thank you. It was a very good talk.
Yeah, thanks.
So one other question. So is there a merit to varying the alpha with the number of samples you draw in the MH algorithm?
All sort of research avenues, excellent research avenues coming up. So you're saying varying alpha is in changing alpha as things go along? Stop. Is that what? Okay. So here's what happens when we do that. When we do that, we can do it. The problem is that this sort of MH algorithm yields a Markov chain transition kernel at the end, right? It gives us a P. It gives us a form of P that's a function of steps 1, 2, 3. If we change alpha at every time step, we are then building a time inhomogeneous Markov chain, right? A Markov chain that is different at every single time point. Now, that's not against the law. You won't be locked up for that. However, your Markov chain may not be ergodic anymore. You don't have the same sort of, I mean, the Markov chain theory is nice and good that you can sort of go back to probabilistic Markov chain theory, get some tools and say, oh, it's a great Markov chain, right? Because you can learn those things. You can depend and rely on probability theory. But now for time inhomogeneous processes, there is more theory in there, but not as much because of the fact that there's now multiple ways of changing alpha. Which way works is unclear. Right? So certainly people have tried it in the past, but the issue is that you essentially have a time inhomogeneous Markov chain. The other thing people use also is use the whole Markov chain history. So instead of just using the previous point, you can use all the journey of the Markov chain so far. That gives you not a Markov chain, right? It gives you something that is M-dependent or N-dependent Markov, nth order Markov chain or pth order Markov chain. That is something called adaptive MCMC, adaptive Markov chain Monte Carlo. Now people have sort of learned and studied when ergodicity could hold sufficient conditions for the Markov chain to be ergodic for that. That's been studied in a fair amount of detail in the last 15 years.
Okay, thanks.
I'd like to advertise here that my student Shiv Shankar, who is also in the audience, he worked on this adaptive drift adaptive MCMC. And yeah, so we were trying to basically prove ergodicity for that. There was no literature available we could find. It was mostly very generic in the sense like, yeah, I mean, whenever you have this adaptive, for example, there's this French group, exactly, containment, minorization, and the things.
Exactly.
So he proved for drift adaptive Markov chains, MCMC, the ergodicity. Yeah.
Lovely. There's another work by Krzysztof Latushinsky at University of Warwick recently where they do something similar. I don't know exactly what you mean by the drift part, but they do something that they sort of categorize as drift adaptive. So maybe
yes, it's basically mean adaptive. So what you do is basically try to go in the direction of the mean of the distribution, and you try to estimate that by using some sort of KL divergence.
Yeah. Okay. Lovely. Thank you.
Yeah, I had one small question. So where exactly was the symmetry of Q used? Now that you're on this slide, I forgot to ask that.
No, yeah, that's true. So here, this is actually f of, in reality, this is f of y, f of xt, q of going from y to xt, and q of xt going to y. So you think of this as, the density of a normal distribution going from y, drawing xt from y, and density of a normal distribution if you're using a normal kernel, drawing from mean xt to whatever the variance is. I used it here to just basically cancel this because the Gaussian distribution, the density function is symmetric. So I used symmetricity just to get rid of those terms, only because, in the next line motivating what's happening in the MH, the Q's sort of get in the way of visualizing intuition. And so it's easier to intuit, that's a word, the MH algorithm if I don't use the Q's and if I assume them to be symmetric.
Okay.
Yeah.
And can you help us with some references where we can read more about all of these convergence of reaching stationarity and all of that?
I'm happy to say some right now, and if you want, I can send them to over by email as well. But the sort of the practice and a little bit of the theory. There's a handbook of MCMC that really is a great compilation of MCMC algorithms. There's from a very, very theoretical perspective, the Bible for theory is Stochastic Stability of Markov Chains by Sean Mine and Robert Tweedy. That's one book. And then the another sort of one place which is a great sort of 2-day read is a paper by Gareth Roberts and Jeff Rosenthal from 2004, which is, I think, a probability surveys paper, which is basically a review of general state space Markov chains. They decided to write that because, in MCMC, we do general state spaces a lot. I mean, pretty much do general state spaces, which are not as abundantly read in the literature as discrete state spaces. So yeah, I think it's a probability service paper from 2004, Roberts and Rosenthal, highly cited, so you'll be able to find it. Yeah, that's a great 2-day read. I mean, of course, you're allowed to take 8 days on it, but it's a great short read.
Okay, thanks a lot.
Mm-hmm.
Dootika, you can also say that you don't want to take other questions and you have other things to do.
No, I'm happy to. I mean, this is the fun part.
This is a great example of interactions working even in the online format of the colloquium. So I'm very glad to see this myself. Are there other questions from the audience?
I have one more question. In high dimensionality, that alpha became very small. So acceptance keep increasing. So this is the problem.
Yes.
How can we approach this?
So right. So two things. Without, I mean, I'm in the danger of saying too much without knowing details of your problem. But as a general rule, that is not always applicable, but still a general rule. Our goal in high dimensions is to tune the proposal so that alpha is about 23%. Okay.
Okay.
That is the general rule that's coming from one of Gareth Roberts's PhD thesis papers to sort of tune to 23% in high dimensions. Now, but practically speaking, this becomes really difficult because in high dimensions, you have to tune the proposal for every component. And that becomes really complicated. So another sort of thing people sometimes do is do variable at a time proposals. So variable at a time MH runs, where you don't propose a whole vector and accept or reject the whole vector together. Because proposing a whole vector and accepting the whole vector requires every component to be compliable and to land up in an area of high probability. Right? Every component in 1,000 dimensions should land up in an area of high probability. As dimension increases, the chances of one component going slightly array increases. So what you could do is do variable at a time. So if you want to, Google or search that, is to variable at a time or component-wise MCMC, where you update, you propose a component for each, proposal value for each component, and accept or reject that, then move on to the next component, accept or reject that, and then move on to the next component.
Yeah, actually I read that paper also. Yeah, okay, thanks.
Welcome. There's another one. I'm a little confused as to how MH and MCMC are connected. Are they different sampling schemes, right? So MCMC is the parent name of the algorithm, Markov chain Monte Carlo. Metropolis-Hastings is a particular example of a Markov chain Monte Carlo algorithm. Okay, there's other Markov chain Monte Carlo algorithms like Gibbs samplers, for example, Metropolis within Gibbs samplers. The Hamiltonian Monte Carlo, which is a new sort of MH, sort of Metropolis-Hastings type sampler. So MH is a particular instance of a Markov chain Monte Carlo algorithm.
Other questions? All right. So just as a last word, I would like to advertise another talk on the 23rd of November by our own Professor Shrikar Vadlamani. He'll be talking about MCMCs in the context of understanding how the monsoons work. So if you found this interesting, then maybe the talk on the 23rd might be a nice follow-up. And let's thank Professor Dootika Vats once again for a wonderful talk and also for patiently answering all our questions. Thank you very much.
I was happy to. Thank you so much for having me. This was really fun.
Thank you, Dootika.
Bye bye. Is it possible for me to sign up to the put me on the mailing list so I can actually attend next week?
I will add you to the mailing list. Yeah, sure.
Okay, perfect. Thank you.
Yeah, I was just wondering if you would be at all interested in other talks which we would have. So should I just send you the announcement for the 123rd?
No, just add me to the mailing list. I mean, I might pop in whenever I find something interesting.